So we're now at our example 2 here. So let's look at our computer screen and read the description of the problem in our example 2. So the description says a sample of 396 cell phone users shows 300 of them are iPhone users. So it looks like we're using the same sample from our previous example. But now let's look at the statement of the question right here. At significance level 0.01 is the sample showing strong evidence that proportion of iPhone users is less than 85%. So after reading the description of our problem in example 2, once again, this problem we're doing is a testing hypothesis problem about the proportion of iPhone users. So first responsibility is once again to identify our hypothesis H sub 0, the null hypothesis, and H sub 1, the alternative hypothesis. Again, as a quick scratch work, but immediately on the computer screen, if we're looking at this statement right here, proportion of iPhone users is less than 85%. This is what we are trying to prove. And so that means, symbolically speaking, we're trying to prove that our proportion value, our population proportion value of iPhone users is less than 85%. And formally, or in decimal, we're having a statement saying proportion of iPhone users is less than 0.85. And this is going to be placed into our alternative hypothesis. So here our alternative hypothesis is stating that, so H1 saying that we're trying to prove that the proportion of iPhone users is less than 0.85%. And so once we have identified the alternative hypothesis, then it's now going to be easy to identify our null hypothesis. We can simply just replace the inequality symbol from our alternative hypothesis with an equal sign. And that statement involving the equal sign here is going to become our null hypothesis. So null hypothesis now reads P equals 0.85. So from our previous example, when the inequality here was greater than we call that testing procedure there being a right tail test. So here in this particular problem, right after identifying our two hypotheses and recognizing that our alternative hypothesis has the inequality being less than or pointing to the left, we are going to refer to this testing procedure as this is the left tail test. And again, allow me to save all the explanation until the very end after we have put together all the steps. And so again, to start into the steps, let's have a look at our screen here. A sample of 396 cell phone users show 300 of them are iPhone users. So once again, we are using the same sample proportion from our previous example. So P hat here is 300 over 396, which is in decimal equal to 0.7576. And of course, the sample size of our sample that we used is 396. And once again, as long as we start picking up a sample, then we must realize that our sample that we have is not the only sample. Indeed, there are infinitely many other samples out there of the same sample size. So the average, where I symbolically refer to as the mu p hat symbol, the average of all sample proportions out there existing together with this sample we currently having. That average should be, in this case, 0.85. And I will give the detailed explanation of how this value came out to be 0.85 at the end of our steps after we have successfully put in all the steps and led it into our final conclusion. But now, taking the fact that our mu p hat equals 0.85, then again, with our p hat value here being 0.7576, but only one sample among infinitely many other samples, then there will be an average spread of all sample p hat existing out there, and we symbolically refer to that as the sigma p hat. And our sigma p hat can be calculated by 0.85 times 1 minus 0.85, and this formula came out from the central limit theorem that we previously learned, divided by the sample size 396. This quotient is to be put inside a square root. Final calculation comes out to be 0.0179. And again, unless being specified otherwise, usually for sigma p hat, I would go with 4 decimal places. And once we've had our sigma, again, remind yourself, the sample we have is not the only sample ever exist out there. There are infinitely many other samples out there. So now with the sample we already had here, compared to its average of all sample proportion values, then our sample proportion here has a z-score. And so the z-score for our sample, again, I use the symbol z sub p hat. And calculating our z-score, we're looking at 0.7576. Subtract 0.85, and as a fraction, I'm dividing by 0.0179. This is just simply the sigma p hat value to be in the denominator. Calculation of mine came out to be negative 5.162011, and a lot longer. And as I keep reminding, unless being specified otherwise, usually for z-scores, any z-score, I would go with 2 decimal places. So in this case, we will round it down to negative 5.16. And again, I need to mention that checkpoint for consistency again. But so, back to the alternative hypothesis. Our statement was reading, we want to prove that our population proportion of iPhone users in general is less than 0.85. And so the consistency that we're recognizing here is that our z-score for our sample is currently showing a negative z-score, is indicating that compared to this value in the claim, then our sample already appeared lower than this claim value. And this claim value is currently the mu p hat value. And furthermore, since we said earlier that even though without much explanation so far, but this kind of test we're about to do is being regarded as the left tail test. And so it is also consistent that our z-score is a negative z-score, the z-score for our sample value. But of course, here I'm only pointing out how consistent the z-score should appear together with being the left tail, but this is not an explanation of what left tail test is all about. And so now into my next step, or our next step. So once we have found the z-score for our sample, again, I am going to find it's all about realizing that our sample is not the only sample. There are infinitely many other sample proportion values out there. then now we want to measure the probability where among all sample proportions of size 396, we are going to run into the sample proportion value that's particularly less than or equal to 0.7576. And once again, another checkpoint for consistency. But so the alternative hypothesis here was having a statement p less than 0.85. And so here, in the way how I'm setting up my symbolic statements to calculate my p-value, then in this probability problem right here, I'm using the left side inequality, the inequality that points to the left side. And again, I'm using the sample value to be in my probability statement. And again, this calculation that we're about to find is being referred to, or the answer that comes out, the calculation that will come out from this problem, from this probability question, will be referred to as the p-value of our sample. And so, once again, let's imagine that if all of our sample proportions can be placed on a bell curve, then this time 0.7576 is somewhere on this bell curve, but the way how this statement is indicating, then we're looking at the shaded area to the left hand side of 0.7576 for wherever 0.7576 being located on the bell curve. But that area is the same as the area on the standard normal distribution, where we're looking for z-score being less than or equal to negative 5.16. So this answer, or in other words, the p-value is also the same as the area on the standard normal distribution curve, where we're looking at z-score less than or equal negative 5.16. And now finding that area is just a matter of simply running our LS&D program that I have been using throughout the entire quarter up to this point. And when LS&D is asking for a z-score, we are going to provide negative 5.16, and we don't need to subtract this from 1. We don't need to subtract this answer from 1 simply because the area that we're finding is already to the left side of our designated sample value. And so on my computer screen here, with my LS&D program currently running, z-score negative 5.16 gives me area to the left being 1.235 E minus 0.7. That value here means our left tail area here is in real decimal 0.000001,2,3,5, which is, as I said, unless being specified otherwise, usually any of these p-value I would round that to 4 decimal places. So in 4 decimal places, our p-value is concluded to be 0.0000, or literally speaking, we can say that we have a p-value. Our sample has p-value 0 in this case. And so now again, but having a p-value successfully calculated, how will that help us decide whether or not our sample is strong evidence or not? Remind yourself that ultimately the question is looking for, is the sample showing strong evidence? that proportion of iPhone users is less than 85%. And so in order to decide whether or not our current sample that we're using is being a strong evidence or not, we need to use this p-value to compare that with the given significance level from the problem. So back to the problem. The given significance level here is being indicated at 0.01. And so now comparing our p-value with significance level 0.01. Apparently speaking, our p-value is well below the significance level again. And so in that way, we are now ready to make our final decision. So observing our p-value of the sample being well below our significance level, our final decision is that our sample is strong evidence. This sample proportion value is strong evidence. For what purpose? We're using that as strong evidence to either to reject the null hypothesis h sub 0, or alternatively we can say we have strong evidence to support h1. And again, looking back at our problem, the description of our problem on the computer screen, then ultimately the format of the question itself is a yes or no question. Is the sample showing strong evidence? And we just now decided that our sample is strong evidence. And so the actual answer to this question now is a yes. Is our sample showing strong evidence? Yes, our sample shows strong evidence. Is showing strong evidence to reject h sub 0 or to support h1. All right, so let's now look at the explanations for the steps in example 2. So we already knew that from reading the wording of our problem in example 2 that we had our two hypotheses. H sub 0 for no hypothesis is claiming that the proportion of iPhone users among the cell phone users community is a 0.85 proportion or 85% proportion. Then we have an alternative hypothesis H1 that's saying P, the proportion of iPhone users, should be generally below 0.85. Okay, and so back in the earlier part of the video where I was showing the steps, then I was saying that this testing hypothesis problem here, this particular testing procedure is being regarded as a left tail test. However, I will in this problem here I will save that for the later explanation. The sample we use is again, and there's only one sample. And this is also, if anyone viewing the video notice that this sample is the exact same sample proportion value that was used in example 1. So in the sample we have here 396 cell phone users. So out of 396 cell phone users, we found 300 of them are iPhone users. And that came down to 0.7576 in 4 decimal places. And of course, our sample here is at sample size 396. And so again, now for me to start bringing in the explanations, then what we use here is one sample. And we only have time and effort to only pick one sample. And so now with this one sample, once we can find a sample or one sample at this given size right here, 396, then anyone picking up a sample must realize that the sample we have is not the only sample. Indeed, at the same sample size right there are infinitely many other sample proportion values right there. And so in that way, again, recall from our days learning about the sampling distribution of a proportion, then we can have a random variable capital P hat. Optionally, I use a subscript 396 right here to indicate that any value of this random variable is the proportion of iPhone users in any sample of 396 cell phone users. And so again, recall from the idea we have learned back in the days that we learned about the sampling distribution of a proportion. Then since this random variable capital P hat 360 has infinitely many values, then there will certainly be, according to the central limit theorem, there will certainly be the mean, because this is well known as a population of data, population of sample proportion values. So now we can have a population mean of all sample proportion values out there. And so this is a mu P hat. And central limit theorem guarantees that mu P hat can always be equal to the actual population proportion. And further, we know that average spreading, or in other words, formally speaking, the standard deviation of all these sample proportion values, sigma P hat, will be equal to our known population proportion multiplied with 1 minus P, the known population proportion again, divided by the sample size, and take all that in a square root. So after this brief reminder about our understanding of the sampling distribution, then now we can bring it into some actual explanation. So for this current sampling distribution, at this point, once we realize that our sample proportion is one among infinitely many other sample proportion values out there, then all we know is the mu P hat should equal to P. But in this case, based on our assumption right here, based on our assumption, h sub 0 is saying P is equal to 0.85. And so now I'm going to start out with this logic, similar to the explanations we've had back in example 1. If we start out by letting h being true, if we were accepting h sub 0 to be true, if this value was accepted, this claim value is accepted as the actual population proportion of iPhone users, then what can happen? What consequently will happen after that? So here I'm starting out by saying if h sub 0 was true, or in other words, you can think of that as if we accepted h sub 0, or accepted this claim value as the actual population proportion, then isn't it obvious that the center, or the population mean of all sample proportion, or in other words, the population mean of all values in this distribution right here, will be consequently 0.85. Because right now, of course, as I was saying, we have only assumed that this was true, assume h sub 0 was true, or pretend that we accepted this value. So if this value really was accepted as the truth, then consequently that population proportion here currently being accepted is going to be consequently based on the understanding of our central limit theorem. It leads to mu P hat, the center of all sample proportion values, must be equal to 0.85. And so in that case, in that way, a further consequence is that, and again, according to the central limit theorem, our average spreading, or formally speaking, the standard deviation of all sample proportion values, average spreading of all sample proportion values from the center here will be calculated as 0.85, the known, the currently accepted population proportion, multiplied with 1 minus 0.85, again this is the currently accepted population proportion, and divided by 396. This is the sample size that we are currently using in our sample. And so now we're particularly, since we are using a sample being as large as 396, then and the entire sampling distribution here, any sample proportion value from this distribution is at sample size 396. And so central limit theorem says that sigma p hat can be 0.85, the currently accepted population proportion, times 1 minus 0.85 divided by the sample size, and take the quotient inside the square root. Calculation comes out to be 0.0179. And as I have expressed many times, unless being specified otherwise, but a lot of these values are being rounded to 4 decimal places. And so before I move on to the next step, I have to emphasize again, this value here, the importance of this value is that this is the average. We call this formally the standard deviation of all sample proportion values. But the actual meaning of that, this is the average, on average, all sample proportion values being different, on average, being different from this center by 0.0179. So we call that this is average spread. On average, how values, all sample proportion values are being spreaded away, being different, being deviated away from this center. And so of course, this is currently the 0.85, the mu p hat is the center of all sample proportion values, because our evidence, our sample we use is one among all of those sample proportion values. And so here's the center, and this value here is the average spread. And again, since our sample proportion value at this sample size is only one sample among infinitely many other samples that we generally regard as the random variable capital P hat 396 here, then at least from what we know about our own sample is that from where it stands and relative to the center of all sample proportion values, then 0.7576 being our current sample, we'll have a z-score. And we are doing that by taking the value of our current sample, subtract the center of all sample proportion values, or namely it's the mean of all sample proportion values. The 0.85 is here, and we are dividing that difference by the standard deviation, 0.0179. This is the sigma p hat that we found previously, or in other words, the average spread. And so the work we're finding here is nothing but just the z-score for our sample. So it's a z-score just like any other z-score. We take the value, we subtract the mean of the data, and divide by the standard deviation. But since this z-score is a little special z-score because it's the z-score particularly for our sample that we're using in this testing hypothesis problem, so I optionally use this subscript p hat. So z subscript p hat is just to indicate, and I only do this as a usual practice when I'm doing a testing hypothesis problem right here. So it's a z-score for our sample being a p hat value. And now calculation comes out for us being negative 5.16. And so just like that, we have seen this step back in the earlier part of the video where it shows all the steps. But now, and so that's how, this is where I give the explanation of how I got that z-score here. And again, as a reminder, unless being specified otherwise, for all z-scores, and including this z-score right here, I am going to be using 2 decimal places. But now observe this z-score being a negative z-score, unlike the problem we've had in example 1. Then this z-score is clearly indicating that our sample proportion value right here, or that value being written here, is below the center, which came out from the claim in our null hypothesis. So the sample is reflecting some reality that's already lower than the value being claimed in the null hypothesis. And on another hand, the sample size that we are using in each of our sample, and particularly in our current sample right here, is being as large as 396. So there are 396 cell phone users in our sample. And so in that way, again, with this sample size, 396, I am going to multiply that with 0.85. So very similar to the explanation I've had in after example 1 right here. This 0.85 is the value that supposedly the population proportion that we're currently accepting. So for now, if we have accepted that the actual proportion of iPhone users is being 0.85, then 396, the sample size that we're using, multiply with this 0.85 right now, as a consequence, comes out to be, calculation shows 336.6, which is a number a lot higher than 10. And further, the same sample size again. And now if we're multiplying with 1 minus 0.85, we're coming out with a value. Calculation shows 59.4, which is also another value quite above 10. And so recall from the central limit theorem that with this sample size that we're using, then what I've just pointed out here is that the sample size we're using, according to the central limit theorem, is just now past the 2 requirements about the 2 requirements for our capital P hat random variable, capital P hat 396, to be successfully on the bell curve. So now recall that I just explained earlier that our sample is one among infinitely many other samples at size 396. And now we have just proven that our sample size passed the 2 requirements to conclude that all sample proportion values at size 396 can be normally distributed. This is indicating we're having a bell curve data. And that bell curve will take center currently accepted. That center is currently accepted to be 0.85. And you can see here, you can see that I repeatedly use the term accepting, because right now we still don't know what the real true value is. But what if we accepted this claim value, the value being claimed in our null hypothesis, as our truthful actual proportion of iPhone users? Then that value can be the center of our bell curve data. And further, the bell curve data has standard deviation 0.0179, as we have calculated in the earlier steps. And so, knowing that all of our sample proportions can be distributed on a normal distribution bell curve centering at 0.85 and 0.0179 for standard deviation, then recall from the earlier part of our video that when I was showing only the steps, then when it came down to calculating the p-value, and of course up to this point I still have not explained why I was setting up the p-value calculation as the probability where we're looking for p hat, capital P hat 396, being less than or equal to 0.7576. I still have not explained that, but at least think about once we got it set up, once we set it up the calculation, then we can now calculate this probability as a bell curve problem, meaning and I did draw this little bell curve back when I was showing the steps here, and here I'm doing it again. This bell curve is having center accepted to be 0.85 because it came out from the claim in the null hypothesis, and our sample is somewhere to the left of this accepted center, 0.7576 here. So this is our sample, this is the claim. But this problem now, this probability calculation setup here now can be calculated as a bell curve problem, where I would shade the area, shade it to the left side of where our sample is on this bell curve. And this is the bell curve for all sample proportion values at size 396. Now the standard methods for calculating this probability is that this area will have an equivalent or an equal area on the standard normal distribution bell curve, where we're looking for a z-score that falls below or less than or equal to negative 5.16. And that's the entire reason why I was showing the step for calculating our z-score previously. And here's a summary of all the steps here again that I was going over just earlier. So the z-score for our sample is negative 5.16. And so this is how it is in our current step. And so at this point, the actual value turns out simply as just, and since being a problem calculating the area shaded to the left of a given value on the bell curve, then it's just a matter of running the LS&D program, as everybody has already knew up to this point of learning in a quarter. And when the LS&D is asking for a z-score, we are providing negative 5.16. And the final p-value comes out. Final p-value came out for us being 0.0000. So the idea, it's not an absolute zero. It's not a value being absolutely zero, but it's a value that's small enough so that in 4 decimal places, that's my reason of showing, a 0 point with 4 decimal zeros right here. But it's indicating that it's just a value, not absolutely zero, but it's a value where even when we round to 4 decimal places, it's still 4 zeros before whichever else comes after that. So that is our final p-value calculation. And so at this point, I need to make a quick recap everything we're doing, and this is, once again, this is just the explanation from each of every single steps I was showing in the earlier part of the video. But in each and every step that we are doing here, including the step calculating the p-value here, is all a consequence from accepting the claim value to be truthfully the proportion of iPhone users. And so currently we accepted that the claim being in our null hypothesis is the truth. And if that was the truth, then consequently it led to all these calculations and eventually down to our final p-value calculation. So what if that value being claimed in our null hypothesis was not true? Then some of these consequences will be conflicting, will hit to a conflict with some reality. And so I will get to that explanation in the following steps. All right, so now let's look at the bell curve representing the distribution of all sample proportion values at size 396. So once again, any value on this line of our current bell curve here is a value to the random variable capital P hat 396. It's a sample proportion of size 396. And this bell curve has a center at 0.85 as argued in the earlier steps. So now Back on my computer screen here, the wording of the problem in example 2 says, in this testing hypothesis problem, we have a significance level given to be 0.01. So just like how I have explained with lots of explanations and details after my worked out steps in example 1, then here the same idea falls out again. On this bell curve, there is a what I so call the common area. Any bell curve has a common area, and the meaning and what the common area is has been explained in the earlier part of the video where I explained about the steps in example 1. But now right here, since our significance level is given to be 0.01, that means this little tail being referred to as the unlikely area, and also the other little tail to the left outside of our common area. Each one of these now is being as large as 0.01 due to our significance level being 0.01. And significance level, once again, as a reminder, being notated as the symbol alpha equals 0.01. And thinking of the significance level as a percentage, then this red area as a right tail right here is being only 1%, and the other red area is being another 1%. So that means the common area is being as large as 98%. And now our sample proportion that we particularly found being in 4 decimal places, 0.7576, is clearly lower than the value being claimed in our null hypothesis. And remind yourself again, our value being claimed in the null hypothesis is being right at the center of the bell curve. And so from where that is, this sample is now clearly below the value claimed in our null hypothesis. However, we want to know whether this sample proportion value, certainly lower than our value claimed in a hypothesis, in a null hypothesis, will be inside the common area or indeed falling outside of the common area, and particularly falling into the left tail area outside of the common area. And for that reason, that we are particularly interested in finding out whether our sample is falling into the left tail unlikely area outside of the common area here. This problem here, this testing hypothesis is being referred to as the left tail test. That's the true meaning of what a left tail test is. And I will explain the reason why we are particularly interested in whether or not our sample proportion falls into this left tail area after I put all the details here together. So now we know that our testing hypothesis for this particular problem here, our testing procedure is a left tail test. Then just like the explanation I deliver at the end of example 1, then now anytime looking at the alternative hypothesis where it says generally we would like to prove the proportion or the value being below what being claimed in this statement, then the inequality lesson right here immediately rings a signal about the problem will be a left tail test. And so we have a way to tell immediately whether or not our testing hypothesis procedure is a left tail test or right tail test, right by looking at the inequality in our alternative hypothesis. And now again, on the bell curve that represents the distribution of sample proportion values at size 396. The p-value for our sample calculated as the probability that on this bell curve we would find a sample proportion at size 396 being less than or equal to 0.7576. So that's how we set it up, the calculation of the p-value. But now remind yourself or recall that this probability calculation as a bell curve problem is graphically understood as an area being shaded to the left hand side, and let's say on this bell curve then 0.7576 is somewhere. And so this, again, this probability calculation is graphically represented by the area shaded to the left, and our sample would be here. And we have seen in the steps, among the steps, that this final p-value came out to be 0.000. And then from this p-value of ours represented graphically as the black shaded area, or the area shaded in black here to the left of 0.7576, we also went further and compare this p-value of ours to the significance level, and we notice that this p-value from where our sample is well below 0.01, which is the significance level. So putting this argument together here, the significance level, I wrote it in red ink, and as now as a graphical representation of that, then 0.01 is the area outside of common area. But since the p-value is less than the red area, p-value is being shaded in black, and the significance level is going to be shaded in red ink, but bigger than the p-value, or in other words, the p-value is smaller than the significance level. That means our black shaded area here has to be smaller than the red shaded area. And even though the red shaded area is already a 0.01, only about a 1%, but our p-value is even smaller than that. So having a p-value, having the black shaded area, and note and recall yourself again, the black shaded area is intended to shade from where our sample is and shade it to the left hand side. So with the black shaded area being completely contained inside the red shaded area, the significance level, then that obviously proves that our p had our sample proportion value being 0.7576 is now clearly, I'm using this term, is clearly among the unlikely values. And so now that p hat is clearly being among the unlikely values, we can make a more powerful statement, a stronger statement. P hat itself is an unlikely value. It means it's in the way how we claim, in the way if we claim 0.85 as the true proportion of iPhone users out there, then 0.85 would consequently be the center of this bell curve, and we have a common area being 85%. Common area being 98%. And we just now have proven that in that way, the sample we found, we already knew that it's below, it's to the left hand side of 0.85, and just now we further found out, we've proven that it's also fell right into the area of among all the unlikely values, or in other words, p hat itself is an unlikely value instead of being in the common area where we commonly get those values near the value claimed in a null hypothesis. All right, and again, just like the argument I have made back in example 1, then here, once the null hypothesis claim a value, so in our case here, this null hypothesis of ours claimed that the proportion of iPhone users equals 0.85. So once the claim was made, then we have learned that the claim became the center on our bell curve representing the distribution of all sample proportion values. So 0.85 is here right in the middle, right in the center of the bell curve. And this bell curve now has a common area being as large as 98%. Okay, and that's a pretty big common area. So again, it means that once the claim was made, and of course samples are allowed, sample values are allowed to be fluctuated up and down from this claim value, because everyone is human being. So once even if somebody claims some value, but we have to allow them a certain amount of fluctuation. But now the common area here means we have already accepted 98% of sample proportion values, including all of those that fluctuated either lower or higher than the 0.85, and we have already accepted 98% of all sample proportion out there, except for those that's being extremely too high, that falls into this right tail area being a 0.01, or except for those that's being unlikely low, extremely too low to the point that we regard it as unlikely samples that fell into this area as unlikely area to the left. And so our sample being 0.7576, once the claim was made, then any sample, including our sample here, is at the moment it's being picked up, this sample is expected at 98% to be in the common area, or to be among the common values. If this claim is true, if the claim that proportion of iPhone users is truly 0.85, then at the moment we pick any sample, including our sample, then it is expected to be at 98% probability. So this is the probability that we're expecting, or chance we expected. So this sample is expected at 98% probability to be in that common area, to be among the common values where the person who claimed this can say, hey, I'm only a human being, so whatever I claim here, your value in the sample isn't too far away from me. That's how a person, after making a claim, can defend him or herself based on seeing any sample. But now we are going to present. But here's the problem. But now, in particular, but p hats that we've used, that we have picked up quite randomly, quite easily, for sure is to the left-hand side. P hat is for sure to the left-hand side of the claim value, but it indeed did fall into the unlikely area. And then ultimately I said, but p hat is an unlikely value. Instead of being in the common area, it fell right in the unlikely area, and it is an unlikely value. And that's why at this point we now can say that because p hat is an unlikely value, sample value, then now we can make our ultimate decision that p hat is showing strong evidence, or itself is a strong evidence. Two, either we can say to reject the null hypothesis. Again, remind yourself, the null hypothesis was saying proportion of iPhone users is 85% of the world. But now our sample now is strong evidence to say that we have to reject that null hypothesis. And now we're going to say, also we can say p hat is strong evidence to support the alternative hypothesis H1, generally saying that the proportion of iPhone user in the world should be generally less than 0.85. And again, with the null hypothesis, claiming that proportion of iPhone users equals 0.85. And our testing of this hypothesis has already concluded that our sample on this bell curve, 0.85 from the claim in the null hypothesis, is at the center of this bell curve. And this bell curve, again, as we have seen in so much explanation, this bell curve has 98% area in the middle being referred to as the common area. So we already show that with the claim being like this, our sample proportion, currently taking value 0.7576, fell right into the unlikely area and making itself strong evidence. And so think about the person who made the claim here. Once that person saw the rejection of H sub 0, because our p hat here shows strong evidence, then the person can make a different claim, where generally this time he or she would bring the claim to a value lower than 0.85. And so let's say now hypothetically, if that claim is being brought to a value but somewhere lower than 0.85, all I know is the new claim here is a value that's lower than 0.85. Then there's still that common area being 98% in the middle, referred to as the common area. But this time, if the claim is being brought down to a different value lower enough and far away enough from 0.85, where p hat would actually turn out the same p hat that we used would actually turn out to be no longer in the unlikely area, but instead now being in the common area, then that's where we would say, so in case like that, if the claim was made where our p hat fall right in the common area, then this is where we're saying that p hat is not strong evidence. And that is another way of understanding our alternative hypothesis, as a statement saying that it is suggests that true proportion of iPhone users should be below 0.85, below 0.85 to some value, so that the sample we currently have here would belong to the common area, no longer being an unlikely sample proportion value.